This video will introduce the concept of feedback. So we start with a plant, so that's a differential equation that has been Laplace transformed, and we denote it with a symbol here g of s, which equals y of s over u of s. So the Laplace transform of the output divided by the Laplace transform of the input. When I write down my block diagrams like this, I'll write the signals in time above each wire, so you see the names of the signals that are going along those wires as a voltage along the wire generally. And I'll write, instead of writing the differential equation inside this box that relates the output to the input, I will simply write the symbol denoting the Laplace transform of that differential equation written in transfer function form. So g of s here and d of s here. So of course g of s represents the Laplace transform of the physical system that we have built that we want to control, and d of s represents the Laplace transform of an electric circuit that we're going to design that relates this signal E of t to this signal U of t. Now we have a summing junction here, so the signal E of t is an error signal. E of t is equal to the difference between the reference signal R of t coming in and the output of interest Y of t coming out the back of the plant right here. And so what we want to do is we want to design the dynamics of the circuit in Laplace transform form d of s to stabilize this system, to control the closed loop system where we have the plant g of s as specified by taking a look at the dynamics of the system that we're looking at. So d of s might be simply a proportional input, a proportional controller, so u is equal to some k times e, so that's a very simple proportional controller. It might be a little more complicated than that and have some dynamics. For instance, a common class of control circuits is the sum of three parts. It has one part which is just proportional, and then one part which is proportional to the integral, and another part which is proportional to the derivative of the input. So it has a P part, an I part, and a D part, or a PID controller. In general, we can design more sophisticated controllers that tune the dynamics of the plant more precisely to do exactly what we want, and that will be the subject of several of these videos to come. And so let's take a look at the relationship between y of s and r of s in the Laplace transform of this setting. So y of s, of course, is just simply g of s times u of s. Where u of s is d of s times e of s. And e of s, in turn, is simply r of s minus y of s. Now we're going to swing the dependence of on y of s over into the left-hand side, so we can write this as 1 plus g of s d of s times y of s is equal to g of s d of s times r of s. And then we can divide by r of s and divide by this coefficient over here, and what we get is y of s over r of s is equal to g of s d of s over 1 plus g of s d of s. For convenience, since g of s d of s comes up a lot, I will often define g of s d of s as simply L of s and call it L of s, and so we can write this as L of s over 1 plus L of s. And so this is the transfer function then from R to Y, from the reference input to the output of the plant. And that is often called the closed loop transfer function. And we'll denote it here T of S. Some texts will denote that H of S. We'll use the letter T of S. Now if we have G of S as a rational function of S is B of S over A of S, where B of S is just a polynomial in S, and a of s is just a polynomial in S. And so g of s is then referred to as a rational function of S, a polynomial over another polynomial. And similarly, d of s is a rational function of S. So y of s and x of s here are going to be taken as polynomials in S. Then we can plug in g of s and d of s into here and clear the compound fraction to get t of s is simply b of s y of s over a of s x of s plus b of s y of s. And so we see that indeed t of s, the transfer function from r of s to y of s, is also a rational function of S. Generally, for a realizable system, so a system that has some component of inertia in it, the rational function of S that we have here will have a denominator whose order is larger than that of the numerator. And so that's called a strictly proper system. Similarly, d of s, which will typically have some capacitance in it, will also have a denominator which is of order which is higher than the numerator. And so it might also be strictly proper. Sometimes it's a good enough approximation to write d of s as a semi-proper system. So x of s, the order of the denominator, equals the order of the numerator. So that's called a semi-proper system. In general, if the system is either strictly proper or semi-proper, we call it proper when the order of the denominator is at least as large as the order of the numerator. So we'll deal with proper g of s and d of s in this class. Occasionally, it's of interest to consider the improper case, sometimes for specifically for the representation of what's going on with d of s, where the order of the numerator is greater than the order of the denominator. And we'll talk about that more in a later lecture. So the fundamental point is that the dynamics of g of s might be bad. They might be unstable, or they might be marginally stable, and so they might have poles either in the right half plane, it's unstable, or poles near the imaginary axis, so it's marginally stable. And so what we would like to do is fundamentally alter the dynamics otherwise expressed by the system by appropriate design of d of s, in other words, the appropriate design of y of s and x of s, such that the transfer function d of s is stable, so that even though the roots of the denominator here, the roots of a of s, are possibly in the right half plane, the roots of the denominator here, a of s x of s plus b of s y of s, are swung over into the left half plane. So that's what we're going to try to do by appropriate design of x of s and y of s. So further our understanding of what's going on here, it's useful to consider the fact that this picture is so far idealized. There are often disturbances that come in, and one place disturbances can come in is on the input to g of s. We'll call those state disturbances. So this will be a summing junction here, plus there and a plus there. And disturbances can also come in, we can model them as coming in right here, and we'll call those measurement noise, y of t. So we have state disturbances, w of t, and measurement noise, y of t. And for simplicity, we can just model them as coming in at those summing junctions. And so then it's useful to consider not only the closed loop transfer function from the reference input to the output y, but several other transfer functions that characterize relationships between, say, the disturbances and the output, or the disturbances and some intermediate variables like u and e, etc. And the several relations that you get following a similar derivation like this can be written, and in all cases, including this one, we see that the formula, if you want a mnemonic, it's just the forward gain. So in this case, L of s is g of s d of s, and so the forward gain from r to y over the loop gain all the way around. So 1 minus the loop gain, And so our loop gain here, as we've defined it, has a negative at this summing junction. So the loop gain here is g of s times d of s times -1. And so this is the mnemonic that helps you to derive the several other transfer functions that relate the inputs and the outputs here. And those several other transfer functions, so we have t of s. I'll just rewrite that one up here. T of s is, again, g of s d of s over 1 plus g of s d of s. And so that's equal to y of s over r of s. And we can write several others. Let me take a moment to do that. Okay, so there we go. And we see here that we have several transfer functions in addition to the transfer function y of s over r of s, which we've already derived completely here. We have other transfer functions, for instance, from the input w of s to the control signal u of s, and the sensitivity called the sensitivity of E of s to R of s. And so if we have a reference input coming in here and we want to say, okay, what does the error look like, which is the same as the transfer function from V of s to Y of s, we can take a look at the transfer function from V of s to U of s, is minus that, and we can take a look at the transfer function from W of s to Y of s. And so it's different relationships between the various inputs to this problem and various signals along this problem. Typically go by these four names: sensitivity, S of s, complementary sensitivity, which is just 1 minus the sensitivity, so we have the sensitivity and the complementary sensitivity are related closely, like that. And we also have the control sensitivity and the output sensitivity as the names for these two things. It's useful to remember these words because these words are often associated with these transfer functions. Note that the loop gain in all of these cases is the same, so we have 1 minus g of s, or sorry, 1 plus g of s d of s in the denominator in all four of these cases, but we have these different cases for the numerator. Okay, so this presents a fundamental challenge because now we see that if we excite the system, say with a sinusoid, so we take s is equal to I omega for some frequency of excitation omega, we see that if we want good tracking, we want t of s to be 1 over a broad range of frequencies. And so the output y matches the input r for a sinusoidal input over a broad range of frequencies. To achieve that, we need y of s over r of s to be about 1. So in other words, we need g of s times d of s to be some large value in order to achieve that over a broad range of frequencies to get good tracking. But we would also like the control signal u to not respond so much to external disturbances that come in w. So we would like the transfer function from w to u to be small if we could get that. You see that we can't simultaneously make that response small and make this near unity. And so there's a limit of what we can do. There's a fundamental performance limitation here, is that if you want to limit this sensitivity, then you can only do that at frequencies that you're not tracking, that you're not getting a good y of s following y of t following the behavior of r of t coming in there. And so you see that there are fundamental performance limitations which limit what you can do with this control effectiveness. There are several more fundamental performance limitations which we will discuss in a following video, but this is just one indication that you can't do whatever you want. And so this gives you an idea of the beginning of the feedback connections. So in the next set of videos, what we're going to do is we're going to first parameterize all stabilizing controllers, first in the case where g of s is a stable transfer function, and then in the more difficult case where g of s is unstable, we can get a parameterization of all stabilizing controllers, and then we will go through the process of classical control design. Is how do we design and tune a good controller in order to stabilize the system, in order to bring all of the closed loop poles into the left half plane and to get a good response from R to Y. And so with that, we'll conclude here, and we'll pick up next time beginning on those topics.